Hello students, welcome back to our next session of light. Today we will be studying laws of refraction of light, Snell's law, refractive index, and let's also see a small introduction of lenses.
What happens when light is incident on the surface of a transparent object? Consider a glass slab and suppose the narrow beam of light is incident on one side. The beam of light partially reflects, partially refracts, and it's even partially absorbed by the object. In the past, we have already discussed laws of reflection. Do you remember those laws? The first one says that the light ray which is incident is reflected in such a way that the angle of incidence and the angle of reflection are equal. And the second one says that the incident ray, the reflected ray, and the normal all lie in the same plane. Just like for reflection, there are some laws for refraction. And what is refraction? Refraction is the change in direction of light as it passes across the boundary separating two media caused by its change in speed. If the refractive medium is optically denser compared to incident medium, then the refracted ray will bend towards the normal. And if it's optically rarer, it will bend away from the normal. Note that the light is incident obliquely on the surface. When the incident light is perpendicular to the surface, it does not change its direction. There are two laws of refraction. Among them, the first one is same as the second law of reflection. Consider light travelling from some medium 1 to another medium 2, which is optically denser than medium 1. So its speed in medium 2 decreases and it bends towards the normal. The first law of refraction says that the incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane. It means that if I were to draw this on a piece of paper, they all will be on the plane of paper and not out of the paper. What about the second law? The second law is also called Snell's law of refraction. Snell's law gives us the relation between the incident and refraction angles and the refractive indices of the mediums. What is the refractive index of a medium? It is the extent to which the refractive medium increases or decreases the speed of light. Mathematically, it is the ratio of the speed of light in the incident medium to the speed of light in the refractive medium. It's denoted by n, and the two numbers in the base are the two mediums. We read this as refractive index of medium 2 with respect to the incident medium 1. Also, V1 and V2 are speeds of light in medium 1 and 2 respectively. We can also define it as the extent to which light changes its direction in the refractive medium. Okay, let's discuss the Snell's law of refraction now. In simple words, it tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the refractive index of the second medium with respect to the first medium. Now look at the term on the right. It is constant for light of a given color and for the given pair of media. This is the basic idea of Snell's law, and there are different ways in which we can understand it. In the previous video, we'd seen what n/1 means. It is equal to the ratio of speed of light in the incident medium to the speed of light in the refractive medium. So we can also say that sine I over sine R is V1 over V2. There's yet another way to understand this. We may want to understand the ratio in terms of the absolute refractive indices of the medium. Absolute refractive index, if you remember, is the refractive index of a medium with respect to vacuum. For instance, if the refractive medium is water, then it's written like this. So can we find this ratio in terms of n1 and n2? Yes, we can. We just use some very basic math. We can write this ratio like this, where c is the speed of light in vacuum. Yes, if you simplify this ratio, we will get V1 over V2. And can you guess what the numerator and the denominator are equal to? That's right. This is nothing but the absolute refractive index of medium 2, and this is the absolute refractive index of medium 1. That was another way of understanding the Snell's law. We can also say that sine I over sine R is n2 over n1. where N2 and N1 are the absolute refractive indices of media 2 and 1 respectively. Hope you understood this well. Let's move on to a new page. So these were the two laws of refraction of light. In the next lesson, we will solve a simple example based on Snell's law. These were the two laws of refraction of light we saw in our previous video. The Snell's law tells us that this ratio is constant and is equal to the refractive index of medium 2 with respect to medium 1. And it is also equal to the ratio of speed of light in medium 1 to the speed of light in medium 2. And that is the same as the ratio of the absolute refractive index of medium 2 to the absolute refractive index of medium 1. Let's try to solve a simple example based on this. Here is the question on your screen. Go through it carefully. We are given the refractive index of glass with respect to air as 1.50. Here, air is the incident medium and glass is the refractive medium. Let us take medium 1 as air and medium 2 as glass. So N21 is equal to 1.50. But what is N21 equal to? Yes, it's equal to speed of light in medium 1 over the speed of light in medium 2. Here V1 is speed of light in air and V2 is the speed of light in glass. But we aren't given any of the two values. We want to find out the speed of light in glass. And for that, we need the speed of light in air. We can write V2 as V1 over 1.5. The value of speed of light in air is very close to the value of speed of light in vacuum. Hence, we can substitute this value in place of speed of light in air. After doing a bit of maths, we will get the speed of light in glass as 2 times 10 to the power 8 meters per second. Don't forget the units. We see that the speed of light in glass is lesser. In the next video, we will talk about an important optical device which is very widely used. Why the faraway objects appear close to us when viewed through binoculars? What are the two transparent materials in front of the binoculars that make those objects appear nearer? And what is that we use to see very tiny things or to read text with small font size? Why do we wear spectacles? What's used in spectacles? The answer to all these questions in one word is a lens. The two lenses in the binoculars make the objects appear nearer to us. We use a magnifying lens to see tiny things and it has a lens in it. And there are two kinds of lenses used in spectacles. We wear spectacles if we are suffering from certain eye defects. If one is suffering from myopia or nearsightedness, we wear spectacles which have concave lenses in them. And if one is suffering from hypermetropia or farsightedness, we wear spectacles with convex lenses. Lenses are also used in telescopes and cameras. So what is a lens? In simple language, we can say that a lens is a transparent material that bends the light in some pattern. The pattern in which the lens bends the light depends on what type of lens it is. Basically, there are two types of lenses: simple lenses and compound lenses. Compound lenses are made up of one or more simple lenses. For the moment, we are only interested in simple lenses. What does a simple lens look like? A simple lens is a transparent material which is bounded by two surfaces in which one of them is spherical and the other one can be either spherical or plane. Yes, one of them is definitely spherical and the other one can be spherical or plane. Let me convex and biconcave lenses. Each one is bounded by two transparent spherical surfaces. Hence the word bi is used. It means two. In a biconvex lens, the two spherical surfaces are curved inwards, and in a biconcave lens, they are curved outwards. One more way to distinguish between a convex and a concave lens is that a convex lens is thicker at the center and thinner at the edges, while the concave lens is thicker at the edges and thinner at the center. Why do we use lenses? What does a lens do? In our previous video, we saw a few examples where lenses are used. In binoculars and magnifying glasses, for instance. But how does a lens function? Well, the main purpose of the lens is to refract the light in some pattern. There are basically two patterns, convergence and divergence. But before studying these two patterns, we first need to understand how the light is refracted by a lens. Consider a convex lens and suppose a ray of light is incident onto it at an angle. This is the normal at the point where the light ray is incident. Now consider a point object here from where this ray is emerging. What will happen when it enters the lens? This ray is travelling from one medium to another at an angle, so after entering the lens, its speed will change, which will result in its bending. Will the speed inside the lens increase or decrease? And where will the light bend? Well, that will depend on the incident medium. Suppose this medium is air. So from this table, we can see that the refractive index of glass is much greater than air. This means that glass is optically denser than air. Hence, the speed of the ray of the light will decrease in glass, and because of that, it will bend towards the normal. Alright, so now what will happen when this refracted ray has reached the other spherical surface of the lens? From there, the ray will be refracted again as it enters another medium, which is air again. You see that this time it bent away from the normal. Can you tell me why? Air is optically rarer than glass, and hence after entering air, speed of the ray increases and it bends away from the normal. And this is how the light ray is refracted by a convex lens. Here only one ray is emerging from the point object, but in reality there are many rays that emerge from this point object and not only one. All these after striking the lens will be refracted in the same way. Did you see something strange? Yes, all the rays meet at a common point. Or we can say that all the rays are focused or converged at a single point. And this is one of the patterns that we were talking about. Convex lens bends the light rays from a point object in such a way that after refraction, all these rays converge at a single point. And this is the point where the image of the point object is formed. If we were to place a screen here at this location, then the image will be formed on that screen. Since the convex lens converges all the light rays at a single point, we also call it converging lens. And
Student, that's all for today's session. Please read the lesson. Take care, stay home, stay safe. Happy learning.